today's video, we'll be looking at our first application of the derivative, known as solving related rates problems. Now, a related rates problem is a problem in which the rate of change of two or more quantities are related. And typically what you want to do is determine the rate of change of one of the quantities, or maybe a value of one of the quantities, given information. All right, and we're going to be looking at several related rates problems in this video. In fact, that's all this video is going to be. For our first related rates problem, let's consider a spherical balloon being filled with air at a constant rate of 2 cubic centimeters per second. We wish to determine how fast the radius is increasing when the radius is 3 centimeters. Well, let's first visualize. So let's say that's our sphere. Right, so the sphere will have a radius r. Now, write down what we know. That is, what are our known quantities? We know that the volume is changing. That means that it's the derivative of volume, dv dt, and that is a constant 2 cubic centimeters per second, and it's positive because it is increasing. Write down what we want to find. We wish to find dr dt when the radius is equal to 3. We now need an equation. Well, since this is volume of a sphere, the equation is volume equals 4/3 pi r cubed. We take this derivative. So dv dt would equal 4 pi r squared dr dt. Notice we're using chain rule, so this is technically implicit differentiation. Right? Both v and r are implicitly defined functions of t, time. This here is the related rate relation. Let's now solve for what we want to find. We want to find dr dt. So dr dt would be equal to 1 over 4 pi r squared dv dt. However, we know dv dt. It is 2 cubic centimeters a second. So that is 2 over 4 pi r squared, which is 1 over 2 pi r squared. We can now solve for dr dt when r is equal to, I believe it was 3? Yes, 3 centimeters. It's 1 over 2 pi times 3 squared. That's 1 over 18 pi. In other words, when the radius is 3 centimeters, it is changing, or in this case, increasing, right, because it's positive. It is increasing at a rate of 1 over 18 pi. Now the units, centimeters per second. For our second example, we're going to take a look at a classic problem in related rates. This is known as the sliding ladder problem. In this iteration, we are told that a 5-meter ladder is leaning up against the wall. The bottom of the ladder is initially 1.5 meters from the wall and slides away from the wall at a rate of 0.8 meters per second, and we're asked to find the velocity at the top of the ladder after 1 second. First, again, try and draw a diagram. We'll say that's the wall. We'll say this is the ground, and we'll let this represent the ladder. Right, so that ladder is a constant 5 meters. We'll call this distance y and this distance x. And so x is the distance that the bottom of the ladder is from the wall. Y will be how high up the ladder is on the wall. All right, write out our knowns. We know that the initial position the ladder is from the wall is 1.5 meters. We also know that the base is sliding at a rate of 0.8 meters per second from the wall. So that is, we're going to keep it as positive. And we're taking this direction to be positive, and we'll take up to be positive. What do we want to find? We want to find the velocity of the top of the ladder, so dy dt, when t is equal to 1. All right, now we need an equation. Well, if we look here, the wall is forming a 90-degree angle with the ground, right? So this is a right triangle. So our equation would be x squared plus y squared is equal to 25. Taking it straight, we get 2x plus 2y dy dt is equal to 0. This was an example in the implicit differentiation. So, I'm sorry, I messed that up. We're taking this with respect to time. So it's 2x dx dt plus 2y dy dt is equal to 0. We wish to solve for dy dt. By doing so, we get dy dt is equal to negative x over y dx dt, right? Subtract 2x dx dt, then divide by 2y. But we know dx dt. It's 0.8, so this is negative 0.8 times x over y. Thus, to find dy dt, when t is equal to 1 rather, this is negative 0.8 times x at 1 over y at 1. Well, there's a problem. We don't know either of those two values. But we do know initial x naught. Well, wouldn't x of 1 be x of 0 right? The initial position plus the velocity times time. So how long it's been traveling, which in this case is times 1. I should change this from 0.8 to this, dx dt times 1. Right? Initial position was 1.5, so this is 1.5 plus 0.8, we get 2.3 meters. To find y of 1, we make use of this equation. So x of 1 squared plus y of 1 squared would have to equal 25, which means that y of 1 would be the square root 25 minus x of 1 squared. Now, in this case, we only take y of 1 to be positive, right? Not plus or minus, because y is measuring a height, right? Height off the ground. A negative value would mean it's below the ground, which is physically impossible for this problem. Now just plug in our known values. So we get the square root 25 minus 2.3 squared. Keep it to 1 decimal place. This is 4.4 meters. We can now find dy dt when t is equal to 1. It's negative 0.8 times 2.3 over 4.4. This is negative 1.1. Units are meters per second. So we say after 1 second, the ladder is sliding down, right? Because our dy dt was negative. The wall at a rate of 1.1 meters per second. For our next example, let's consider a rocket being launched so that it rises vertically. A camera is positioned 5,000 feet from the launch pad. When the rocket is 1,000 feet above the launch pad, its velocity is 600 feet per second. We wish to find the necessary rate of change of the camera's angle as a function of time so it stays focused on the rocket. Okay. So let's try and picture this. We'll say this down here will represent the launch pad. Right, so then draw our rocket. And just a crude drawing of a rocket. And we'll say this is like the flames of the rocket, right? Okay. We'll represent this distance with h, right? We'll represent, say that's the height of the rocket. Now let's say that we have a camera. Again, just a crude drawing of a camera. I don't know, let's say that's the camera. And we know it's a fixed distance of 5,000 feet from the launch pad. We have to determine theta, right? So this is a horizontal. We'll call this L, the distance the rocket is from the lens of the camera. Let me draw that line a little bit better. Then this is the angle theta. Now, by the way, these have to be the same, so we can also say that is 5,000. Right, and then this would have to be the same as well. And we can say, oh, look, that is a right angle. Okay. Now, write this. Let's re-represent this, but now strictly as a right triangle. Right, so there's our right angle there. This is representing our theta. This distance here we know is 5,000. This is an h, and then our hypotenuse will represent with L. Our known values. We know that the velocity of the rocket when it is 1,000 feet off the launch pad is 600 feet per second. We wish to find the rate of change of the angle theta 1,000 feet off the ground as a function of time. Well, we need an equation to relate theta with h. Well, that equation, tangent of theta is equal to h over 5,000. This means that secant squared of theta d theta dt is equal to 1 over 5,000 dh dt. Which means that d theta dt itself is cosine squared of theta over 5,000 times dh dt, which would mean that our value of interest, d theta dt, when h is 1,000 feet, is cosine squared of theta evaluated when h is 1,000 over 5,000 times dh dt when h is 1,000. Now we already have this dh dt value, right? That was the 600 feet per second. We have to determine what this value here is. First, let's find cosine theta when h is 1,000. That would be, using this triangle, 5,000 over the length when h is 1,000. Oh dear, now we don't know that. Well, we kind of do, right? This L has to be the square root of 5,000 squared plus h squared. But h is 1,000, so this will be the square root of 5,000 squared plus 1,000 squared. This comes out to be 5 over the square root of 26. So we can now plug it in. Say that d theta dt, when t is 1,000 feet, not t, I'm sorry, when h is 1,000 feet, is cosine squared 25 over 26 divided by 5,000 times 600 feet per second. This winds up giving us 3 over 26, and the units are rads per second. Right, so when the rocket is 1,000 feet off the launch pad, the camera's angle needs to be changing at a rate of 3/26 rad per second. As our final example, let's take a look here. Water is draining from the bottom of a cone-shaped funnel at the rate of 0.03 cubic feet per second. Height of the funnel is 2 feet. Radius at the top is 1 foot. We wish to determine the rate at which the height of the water in the funnel is changing when it is currently half a foot. All right, so cone-shaped funnel, we'll do something like this. It'll look something like that, let's say. And of course, since it's a funnel, it's going to drain out like that. What we're going to do is draw an imaginary vertical axis straight up through the center of the cone. Radius is 1 foot. All right, so that's this distance here. That doesn't look good. So we'll say this distance is 1 foot. Let's say that this is the current height of the water. We will represent this radius at water height as r. We represent this distance as the height of the cone. And so right there, that is 2 feet. Then we'll represent the height of the water here as h. We know that the volume is changing, it is decreasing at a rate of 0.03 cubic feet per second. We wish to find the rate at which the height of the water is changing, so dH dt, when the current height of the water is half a foot. Our equation, volume of a cone is 1/3 pi r squared h. Now there's a problem. Right, this is given in two unknowns, r and h. We wish to write this in only one unknown. Specifically, we want to relate v to just h, right? We want dv dt to be related to just h. To do that, we're going to make use of similar triangles. Right? If we look, we have two triangles. This one here, 1, 2, and the hypotenuse, and then this one here, r, h, and the hypotenuse. Using similar triangles, the ratio of r to h has to equal the ratio of r to h of that larger triangle, so 1 to 2. This gives us r as h over 2. What we do is we now plug this in to this r here, and we find that volume is 1/12 pi h cubed. Then dv dt is 1/4 pi h squared dh dt. So dh dt is 4 over pi h squared dv dt. But we know that dv dt is a constant negative 0.03. So this is actually negative 0.12 over pi h squared. Therefore, dh dt, when h is half a foot, would be negative 0.12 over that pi 0.5 squared, and this winds up being negative 0.48 over pi feet per second. Right? So the height of the water is decreasing, again, because it's negative, at a rate of 0.48. That's a terrible looking 8. 0.48 over pi feet per second when the water height is half a foot. So when solving a related rates, the idea is to try and draw a picture, right? You want to visualize it. Write out your knowns. Write out what you want to find. Write out your equations, and then go about solving it. That concludes this video on related rates. In the next video of the series, we will continue our study of applications of the derivative by looking at differentials and the linear approximation.